In this video today, we are going to see about linear transformation, the definition, sum and properties. So, first the definition, linear transformation, you call T from one vector space V to another vector space W as a linear transformation if for all x and y in V and a scalar C from F, T of x plus y is Tx plus Ty and T of Cx will be C into Tx. So when these two conditions are satisfied by T, then you call that function T from V to W as a linear transformation. Now based on this given function, we will check whether it is a linear transformation or not. It means if the function T satisfies these two conditions, it is a linear transformation. Otherwise, no. So in the first one, we are taking T from R square to R square, which is defined by T of A1 comma A2. You consider two components here because it is R square. Had it been R cube, we would have taken three components. And it is again going into R square. So again, you will have only two components on the other side. So your input is A1, A2. When you apply T, your output will be 2A1 plus A2 comma A1. Now we are going to check whether T is linear. Now let us consider two elements from R square and one element C from F. Now they are elements of R square means they will have two components. I am taking it as X as A1, A2 and Y as B1, B2. Now X plus Y we will show that will be equal to Tx plus Ty. T of X plus Y is Tx plus Ty. So for this, first let me find out X plus Y. So how do I find X plus Y? The first component will get added to the first component. So it is A1 plus B1. Second component added with the second component, A2 plus B2. Now apply T on X plus Y. So I am applying T on this element. When I give the input as A1 plus B1, A2 plus B2, my output will be 2 times the first component plus the second component, first component. So 2 times the first component plus the second component, this first component as it is. So it is 2 times. Now use distributive property. So I will be able to get 2 times A1, 2 times B1 plus A2 plus B2, A1 plus B1. Now this we are trying to write it in the form in this pattern. That's why they are writing it as 2A1 plus A2. Then 2B1 and then with B2, 2B1 plus B2 and then this A1 plus B1. So that I am writing it as 2A1 plus A2 A1 plus 2B1 plus B2 B1. But by definition, this is T of A1 A2 and this is T of B1 B2. But what is my A1, A2? X. B1 B2 is y. So we started with T of x plus y. We are able to show that it is equal to Tx plus Ty. So the first condition is satisfied. Now we go to the next condition. T of Cx, I will prove it is equal to C into Tx. So C into x. So this is x. Multiply that with C. All components gets multiplied. So it becomes CA1, CA2. So T of CA1, CA2. Now this is my input. Now I am going to apply T. As we apply T, your answer will be 2 times the first component plus second component. 2 times the first plus second, first component as it is. Understand the definition of T here. This is how T is defined. So that I am applying it here. Now you see that C is common in both the components. It can be taken out. Write the remaining and whatever you have there is T of A1, A2. But A1, A2 is X. So it is T of, we started with T of Cx. It is equal to C into Tx. Therefore, my T is linear. Two conditions are satisfied. Hence, the given function is a linear transformation. Next one again. R square to R square, t is defined by t of AB equal to 2a minus 3b, comma a plus 4b. So this part you have to remember correctly because everywhere we will be applying this definition. See, sum to sum the t definition will vary. Your input is a comma b. When you apply t, your output will become 2 times first component minus 3 times second component. That is your first component. Okay, comma this next part will be first component a plus 4 times the second. Okay, so now let us consider x as a b, y as c d. Let us find out x plus y and then we will apply t. So when I apply t on x plus y, what happens? Remember this correctly. It is 2 times the first a plus b minus 3 times the second b plus d, comma first component plus 4 times the second component, 4 times b plus d. Now expand it and collect it properly so that you are able to get it this way. So it is 2a minus 3b, comma from here I am writing a plus 4b and then the remaining 2c minus 3d, comma c plus 4d. So this is T of AB and the other one is T of CD. But AB and CD are X and Y. So we are able to get T of X plus Y equal to Tx plus Ty. Same pattern, T of alpha X, alpha into AB is alpha A, comma alpha B. Apply the same one with alpha there. So this is what you have. And alpha is common in both. I can remove outside. So what I have is alpha into 2a minus 3b comma a plus 4b, but that is nothing but t of ab, but ab is x. So what you have here is t of x. So alpha into t of x. We started with t of alpha x. We are able to get alpha into tx. Therefore t is linear. Next one. T again defined from r square to r square. T of xy equal to e power first component comma e power second component. Again we are checking whether t is linear or not. So now let us take it on t of x comma y. This is the definition. Let me take some u and v in r square, two vectors from the first vector space. So I am taking u x1 y1 v x2 y2 and we are going to find t of u plus v. So let us first find out what is u plus v. So I am adding u and v. It is x1 plus x2 comma y1 plus y2. But when I apply t, it becomes e to the power first component comma e to the power second component. Now e to the power x1 plus x2 can be written as e power x1 into e power x2 and e power y1 plus y2 can be written as e power y1 into e power y2, which you can break and write it in this pattern. But what you have as the first one is t of u and the second one is t of v. Now the next one, t of alpha u. So alpha to be multiplied with u, x1, y1. Both components get multiplied with alpha. So alpha x1, alpha y1. So now this will be equal to e to the power first component, e power alpha x1, e power alpha y1. So this can be this is not equal to alpha times t of u. Alpha, you can't take alpha outside common. Okay, so it can't be written as alpha times t of u. Therefore, t of alpha u is not equal to alpha tu. Hence, your t is not linear. Now we discuss some simple properties of linear transformation. Whenever t is linear, when you apply it on 0, what you are going to get back is only 0. So t of 0 equal to 0. Now t is a linear function transformation. Therefore, we know that t of x plus y is tx plus ty and t of cx equal to c into tx. We use the definition. Now this, let us consider the left hand side t of 0. Okay, 0 can be written as 0x, and this can also be written as 0 t of 0. You can write it as 0 t of 0. Now, from this, what can you conclude? T of 0, the answer is going to be 0. Is that okay? Here, I am using the property as 0, this t of cx equal to c into tx. So 0 into tx, or my t of 0, when I multiply, what I get is only 0. So t of 0 is equal to 0. Next property, t of cx plus y is ctx plus ty. That scalar, whatever you have, that can be written outside. So now this is what you have as a linear transformation. These two are true. Now let us start with the left hand side. T of cx plus y. Now this is same as I am applying the first condition. It is t of the first plus t of the second. So it is t of the first means t of cx plus t of the second one ty. Now t of cx is c times tx, and this ty I am writing as it is. So when I assume that it is a linear function, I am able to get this result if part. Now we prove the converse part only if and only if. So the converse part, I will assume this and show that t is linear. So let me consider this. Now in this, put c is equal to 1. So I get t of x plus y. What is t of x plus y? It is 1 into tx plus ty, or tx plus ty. The first condition for a linear transformation is satisfied. Now, second case, I am considering t of cx plus 0. What is t of cx plus 0? C into tx plus t of 0. Just now we proved that t of 0 is 0. Therefore, I am able to get t of cx equal to c into tx. How did we get this? We have taken the second part y as 0. That's all. Okay. So, both conditions are satisfied. Therefore, it is a linear transformation.